Okay. So last okay, we're going to pick up where we left off last time. We started at the topic of limits. And we were just going through a few examples. We're going to continue. So we had some important ideas last time I just want to remind you about. The limit as x gets close to a is the y value that you approach as x gets close to a. Right? So it cares about closeness. Closeness is the idea. We don't actually care about being at the point. Just approaching the point, getting closer. So it means your function doesn't even have to be defined where you're taking the limit. We actually don't care. We just care about how close we can get to that point. We also know that we also talk about one-sided limits. Right. So this is the idea of approaching x from the left of a function. This is from the left. This means your values less than your x values are less than a certain number, so you're approaching from this side, versus approaching a number from the right side. This is from the right. So you let your x values approach from the right side of a number, and you track the y values, and you kind of figure out what the answer is. We also figured out that the limit as we approach a number only exists if both of the one-sided limits exist and they have to be equal. So the idea is the limit is trying to track the unique y value that you approach when your x approaches something. So it means that both sides have to match up. If you're approaching two different y values, you can't say here's the y value. Right? We need some kind of unique answer. We also learned that there are times when infinity can be an answer, even though it's technically not a number, but it will be a kind of behavior that we'll want to be able to track or figure out when that actually happens. So those are just some of the important ideas that we were illustrating last time, and we're going to do some more of these and talk about strategies and approaches that you can have for these problems. So hopefully that's understood so far. Here's the notation for a limit. We also introduced that last time. So it says the limit as x gets close to a would be a number. If it has a superscript, that sign can tell you direction. No superscript means you're talking about overall limits, and you write the function right beside it. You say you're taking the limit as x approaches a of f of x. So that's how we read it. Last time I think I only showed you pictures. I didn't really give you any formulas to work with. So let's actually look at a formula. What if I consider this function? So that 1 over x. There are a lot of lessons we can learn from 1 over x. Find the following. So at any given time, you want to remember the limit is just the y value you're approaching when your x value is getting close to some number. And it only works when both sides match up. So that's kind of how you want to think about things and approach it. Let's do 8. What is the limit as x approaches 1 of our function 1 over x squared? 1 over x. What do you think the answer is? What does the y value get close to when x gets close to 1? Well, as x gets close to 1, this formula will get close to 1 over 1, right? It's just going to be 1. You can also see this from the graph. Notice that on this graph, when your x value is 1, the corresponding y value is also 1, right? So whether you're approaching 1 from the left side, it means you're on the graph getting close to 1 from this direction. Your y value is getting close to 1. If I'm approaching 1 from the right side, I'm on this side of the function approaching that point. My y value also gets close to 1. Right? It stands to reason here that it seems that if I have a function and I can actually plug in a number, I can literally just plug in the number and find the corresponding y value that I need. Right? That's going to be the y value I'm getting close to as I approach 1. It's going to be the y value 1. Let's move on to part B. B asks, what about x approaches 2 from the right of 1 over x? What do you think the answer is going to be? Huh? A half? Well, let's look at the picture before we look at the formula. You can have several ways to analyze something. Okay? So I know here's 2, right? I know it has some corresponding y value. This 2 with a little plus sign in the top right corner means I only care about approaching from the right side, right? Which means I'm a little bit bigger than 2 and getting close to 2 from this direction. So if I'm on this graph and I'm getting close, and the x value is getting closer to 2, what is the y value getting close to? Well, it's going to be close to the corresponding y value for x equals 2. That will actually be a half. Right? Now it turns out, if I came from the left, I'll also get a half, right? That means the overall limit exists, but in this case, I just asked for the limit from the right. C. What about the limit as x approaches 0 from the right of 1 over x? Again, let's look at the graph, try to figure this out. Now we're approaching 0. Why does it not exist? Huh? What's undefined? I'm saying from the right. Right? 0 plus means approaching 0 from the right.
It doesn't approach 0.
What do you mean it doesn't approach 0?
Isn't it not every x of the y?
Sure.
I think
That's actually true.
Can't you not have 1 over 0 anyway? It's undefined.
Correct. 1 over 0 is undefined. That's not what I'm asking you, though. I'm asking what is the limit as x approaches 0?
Is there supposed to be the y-axis? The y value isn't.
Yeah, I want to say, what is happening to the y values when I get close to 0 from the right side?
Well, so the asymptote, so it doesn't approach it.
It's getting closer to infinity.
Yeah.
Of course I'm getting closer to 0, right? As long as I'm not at 0, at any space I move, there will be a corresponding y value to that number, right? At 0, I never actually touch 0, but remember, I have that point right here that we don't care about being at the point. I'm not asking you to divide by 0. You knew from day one that that's a no-no, right? Limits do not care about being at the point. The limit doesn't actually care about plugging in 0. The limit cares about getting super close to 0, right? You never actually have to get there, right? And in this case, we actually can't get there because it doesn't make sense to divide by 0. So the limit doesn't care about being x equals 0. The limit cares about what if it's 0.01 or 0.0001 or 0.0001. What if I get as close to 0 as I possibly can? What is happening to the y values, right? Well, look at what happens as you're approaching 0. At first, the y value is here. Okay, go a little closer. What happens? The y value is here. Go a little closer, the y value is here. Go a little closer, the y value is here. Now, if you start to, let's zoom out a little bit so you can kind of see the idea I'm trying to get to. So now it's a huge scale. You know, this is like, this is 1 over x. So this is like y value 1 billion. Right? So at some point I'm here, this is my y value, like 10, right? Get closer, this is my y value, like 50. You know, get closer, this is my y value, like 300. But notice that the closer I get to the 0, what's happening to my y values? They keep getting bigger and bigger and bigger. Will this process ever stop?
No.
Right. As long as I don't hit 0, the process is never going to stop. I will keep getting higher and higher and higher. So how can I express the idea of getting bigger and bigger and bigger and just keep getting bigger and bigger and bigger, never stopping? We say infinity, right? So it's not an actual number, but it's a way to track the y values. Someone asks, what's happening to the y values? You can definitely give them an answer. You can say, they keep getting bigger. They never stop anywhere. They never get close to any number. They just keep rising. They keep getting bigger. Right? So infinity is a possible answer for us in this class because we'd want to know when something is growing without bound. If something is getting out of control, we'd want to know it's getting out of control. With that in mind, let's go to part D. What if I ask the limit as x approaches 0 of 1 over x? What do you think the answer is there?
Same thing.
It does not exist.
How would you say that?
It does exist.
Is it negative?
Both, right?
It's negative infinity, positive infinity.
How can it be both? So again, let's look at the graph. We've already actually looked at one side of 0 already, right? We looked at approaching 0, never actually getting there, but getting close to it from the right side. And we see that when that was going on, the y values kept increasing without bound, right? I kept going up and up and up, and so we said, as I approach 0 from the right side, the answer was infinity. Now apply the same kind of logic to this side. What's going to happen? Well, as I get close to 0 from this side, the y value actually keeps decreasing, right? So it seems here a valid answer would be to say if I'm approaching from the left of 1 over x, the answer seems to be negative infinity, which means I'm getting smaller and smaller numbers. Over here I'm getting larger and larger numbers. Could you say that these connect, or they're going to the same kind of thing? The answer is no. Does not exist. Because the left and the right aren't doing the same thing. Right? This is the idea of the one-sided limit. Okay, let's look at another situation. What if I ask you this? What is the limit as x approaches -2 of that function? What would you say the answer is?
It would be the same, do not include minus two. Because if you put like negative two into the denominator x, it would be 0, so then it would be the same result.
Not necessarily. Remember, the limit doesn't care about being at the point. So I don't actually care about being at negative 2, just super, super, super close to negative 2. Right? So let's pretend that I never actually get to negative 2, but I'm getting super close to it, like minus 2.000000001. Is there something that the y value is approaching? Any ideas? Hmm?
Factor out the numerator.
You'd be able to draw the graph.
Factor the numerator. What would that be?
X plus 2, x minus 2. You cancel out the x plus 2.
X plus 2 times x minus 2. Right, it's a difference of squares. You cancel those. Okay, what could you say now?
Be negative 4.
So here I'm at x minus 2 is this new function, and so you're saying this is getting close to negative 4. Does it make sense to do that though? I mean, it seems pretty convenient, but does that actually make sense? Well, let's examine it. What does that graph actually look like? Right, let's say I gave you the to graph this function, x squared minus 4 over x plus 2. What would that actually look like? It's not a parabola. It doesn't have the form ax squared plus bx
Isn't that a
plus c.
linear equation?
It's not linear either. Well, not as in that
Yeah,
form,
not
which is linear. So obviously we know division by 0 is a no-no, right? So I can actually think of this in two cases. Maybe sort of think of it as a piecewise, for example. So I know that it's undefined clearly if x is actually equal to minus 2. That's bad, right? So I know at minus 2, craziness happens, I can't actually give you a value. But what if x is not minus 2? Then how can I look at this function? Now, as long as x is not minus 2, this fraction will actually make sense. I will actually have a number on the top and a number on the bottom, and the number on the bottom won't be 0, right? Since it's a fraction, it means I can cancel common terms, right? Any fraction I can reduce if it's possible. It turns out that the top here, I could write as this. And as long as this guy is not 0, that's fine. I can cancel it. Cancellation law, right? So it turns out that this function will actually behave like that straight line, except at that point, right? At that point, craziness happens, but every other point, it's a regular, it's a normal fraction that I can use arithmetic on. So what's actually happening here, if you look at the picture of this guy, draw this y-axis over a little bit. So here's my y-axis, that's my x-axis, negative 2 is over here, right? Now I know that's a bad point, I can't actually touch that. But at every other point, it's a regular, the numbers I'm getting is a regular fraction that I can just cancel stuff, right? So it's going to behave like x minus 2. Now x minus 2 is going to look like what? Maybe I didn't put this over. What does x minus 2 look like? Y equals x minus 2. Hmm? Y equals x minus 2 is what kind of function? What kind of graph?
Linear.
It's linear. Okay, what else can you tell me about it? Where is it? It crosses what?
Y and negative 2.
Right, so negative 2 would be the y-intercept, right? That would be the mx plus b. The negative 2 would be the b. So the graph would look something like this, right? Passing to the -2, right? With +1 slope. Now, everywhere except at -2 it behaves like this. What happens at -2, right? If I trace down an x value here, what would happen there? Well, literally nothing. I'd have to put a hole in this graph, right? So at that point, at -2, I don't know what's going on. The graph doesn't exist. That's division by 0. But everywhere else, it's just a normal fraction. So I can reduce a normal fraction, and I would end up with the graph of a straight line with a hole in it. That's how it's going to actually be different. So now, this graph is not exactly the same as the graph of x minus 2, right? That graph has one thing missing. It has one point missing. The point where I divide by 0, that can't happen. Now, if you think about what a limit is, I don't actually care about being there. I care about getting close to there, right? I care about approaching it. And if I'm approaching that point, what is the y value going to approach? Well, the corresponding point down here, right? But this point is lying along the straight line x equals -2, which means I can sort of pretend that this point was filled in, find the corresponding y value, which it will actually be doing before. So I can see this point isn't actually there, because division by 0 happens there, but I don't care about actually being at that point. I just care about getting close to it. Right? So this is actually a valid thing to do, right? Not in general. In general, I cannot think of this as being the same as that, because it's not. But as far as a limit is concerned, they're the same thing, right? Because I don't actually care about being at that corresponding x value, just getting super close to that corresponding x value. So that's one of these nuances. You might be tempted to start just plugging stuff in, but it doesn't always work in this example. And of course, there are cases where we have like infinity coming into the mix. So let's actually come up with some sort of strategy here so we kind of know how to approach these things. Just wanted to get you guys used to the idea of how you want to think about limit problems. So let's talk about a strategy. So suppose we want to find the limit as x approaches a of some function, right? Here's the first thing you're going to do. Plug in the x value. Try to plug in the x value. The if possible is the important part there. And compute the corresponding y value. This is your answer. That would be it. So you can literally say the limit as x approaches a of f of x is just going to be the function evaluated at that point, right? That was the situation that we were in when I asked you to approach x equals 1 of 1 over x. It was just possible to plug in 1, so I just plugged in 1, right? And if you're faced with any limit problem, that's the first thing you're going to try to do. Can I plug in the x value? Right? That's the easiest way to figure out what the y value is getting close to. If this does not work, move on to step 2. Right? As in this case, it would not work, right? So I'm faced with this problem on a test. I'm like, okay, it's a limit problem. What am I going to do? Plug in the x value. That's the first thing you're going to try to do. But then you're going to realize, can't actually do that because I divide by 0, right? That's actually illegal to plug in the x value. So it means step 1 just wouldn't work. So you move on to step 2. Try to simplify so that you can plug in the x value. Right? That was the strategy that we used for this one. Right? So I'm given this problem on the test. Right? First thing I'm going to try to do, plug in that x value. Can't actually do that because I divide by 0. So what do you try to do? Simplify it. Right? Because what could possibly be the case is that that graph behaves in a certain way, except for one little point. It messes up at that one little point, but I don't actually care about that one little point. Right? So what I can do is simplify. Then here I end up with a case where I can actually plug in the x value. And in that case, that's going to give me the answer. Right? Is it possible? This is your answer. Or I should say the corresponding output is your answer. Right? Because the limit is always talking about the y value. So that's actually what we use on limit as x approaches -2 of x squared minus 4 over x plus 2, right? I couldn't plug in the x value right away, but I didn't give up. I simplified, and I ended up with something where I could plug in the x value. Plug in the x value, that's actually going to be my answer. But what if that doesn't work? Because it doesn't have to. Step 3, right? So there are some cases that are really nice cases where you just plug in the x value, you get the corresponding y value, you're done. That's your answer. There are other cases where you can't plug in the x value right away, but you can simplify so you can plug in the x value. And if you can, that's going to be your answer. What if neither of those work? One of 3 things will happen. One, you will have that the limit as x approaches a of f of x will be infinite. It actually won't give you a numerical answer, but it could give you an infinite answer. 2, the limit as x approaches a of f of x might be negative infinity. You might not get a number, but you can have an infinitely negative number as the answer. Or 3, the limit just doesn't exist at all. So if 1 and 2 don't work out, you're faced with one of 3 possibilities. It's either going to be infinity, negative infinity, or it's not going to work. It's just, I cannot salvage it. Let's actually illustrate. I'm going to give you one that doesn't work out deliberately for the first 2 steps. So like this guy. Limit as x approaches 0 of 1 over x squared. Similar to 1 over x, but I just squared the x now. Now let's see what's going to happen here. Faced with limit as x approaches 0 of 1 over x squared, first thing I'm going to do, try to plug in x equals 0. Whoops, can't work. Right? You have division by 0. So that's out of the question. Let's go to step 2. Try to simplify. Obviously having the x in the bottom is making a division by 0. So is it possible to cancel the x in the bottom? Not with a 1 on the top, right? There's no way I can simplify this. I can't factor anything to cancel that x, right? I can't do anything about that. Whoops, doesn't work. Right? I do not have an option to simplify this, which means I'm now in step 3. Now, how do I figure out which one of these is the actual answer? Is the answer infinity or negative infinity, or it just doesn't exist at all? What do you guys think? How do we approach that situation? Draw the graph. Right? There must be a reason I asked you guys to draw so many graphs in this class. What would the graph of 1 over x squared look like? How does it look? Someone pick these there. Huh? 1 over x squared? What does it look like?
That's artificially rare. That's the negative square.
Sure, yeah. How does that help you to graph it though? You guys need to know your graphs. 1 over x squared looks like this. Okay, so now that we know the graph, can you tell me what the answer is going to be? So 0 is the point we're approaching. So let's say I'm getting close to 0 from the right. What's going on? The y values are just increasing without bound. So the limit on the right side of 1 over x squared is giving me positive infinity as the answer. What about if I'm approaching from the left side? My y values are actually behaving the same way. They're increasing without bound. My limit as x approaches 0 from the left side of 1 over x squared will also give me positive infinity. Can I make any conclusion about the limit as x approaches 0 of 1 over x squared? Positive infinity. Both the left and right side agree, right? They don't give me a number, but they agree that it's increasing without bound. They're both going to positive infinity. Positive infinity is actually the answer here. So I figured out which case in case 3 is the answer. And I figured it out by graphing. You might not always want to graph something though. So in case 3, some possible strategies are: one, graph. Right? If you know what the picture looks like, you can see what the y value is doing. You can just look at it and tell. You know it's either going to be infinity, which means you're going up everywhere around that point. Negative infinity would mean your graph just keep going down everywhere around that point. And not exist means the left and right are doing something different. You can look at the picture and tell when one of these are happening, right? Right, now I know that once I'm in step 3, agree means they're either going to both give me positive infinity or negative infinity. So I know they're either going to agree on one of these two, right? And if they do agree on one of the two, that's fine. Right? What if the thing is complicated and you don't know how to graph, or you forgot how to graph it? As a lot of you actually forgot how to graph 1 over x squared. Use the idea of approaching, right? So what you can do is you can plug in some numbers closer and closer to x equals a, and track your y values that way in a table. It's a very clumsy way to do things, but it'll get the job done. Odds are in 205 you'll never actually have to do this. If you end up doing this, it's because you forgot how to draw something. that just shouldn't happen, but if worse comes to worse and you blank out on a test, you just start plugging in numbers. So for example, and especially if you want to see if things are going crazy, you can even start with very small or very big numbers, right? So you look at something like, here are my x values, here are my y values, taking my y to be 1 over x squared. Now I want to get close to 0, so let's start plugging in some numbers that are close to 0. What if I start with 0.1? What would the corresponding y value be? Remember, 0.1 is 1 over 10. Right? Well, my y value is actually going to give me what? It's 1 over x squared, which means it's going to flip this and then square it. It'll actually give me 100 as an answer. Okay, so what if I said, when a little closer to 0, 0.01, what will happen then? This guy's going to flip it and then square the answer. It'll actually give me 10,000. What about 0.001? It's going to flip it and square the answer. That'll actually give me 1,000,000. Clearly, these numbers keep getting bigger and bigger and bigger. I'm approaching infinity, right? Clearly, the closer I get to 0, when I flip it and square it, the bigger the number is going to be. Because the closer I get to 0, the larger the denominator is going to be. That's 1 over 100. This would be 1 over 1,000, right? The closer I get to 0, the bigger my denominator is. So when I flip it, the bigger that number is going to be. Clearly, this list is just, it's going to start increasing out of control. Now, what if I approach 0 from the other direction? What if I approach 0 from the negative side? Let's say minus 0.1. Exactly the same thing is going to happen because I'm squaring. I don't care about the sign. Plugging in negative 0.1 is exactly the same as plugging in 0.1. So that's going to be 100. What if I plug in negative 0.01? Well, that's going to give me 10,000. If I plug in negative 0.001, well, that's going to give me 1,000,000. So I know if I approach from that way, I'm still going to positive infinity, right? So I can see whether I approach 0 coming from the positive side or the negative side, they're both going to infinity. In the case of 1 over x, it didn't work out that way, right? So let's say, I don't know, pigs fly and you forget how to graph 1 over x or something, right? Now if you look at this kind of chart for 1 over x, if you start with 0.1, well, this is just going to flip it. You're just going to get 10. Start with 0.01, this is going to flip it, you're going to get 100. Start with 0.001, this is going to flip it, you're going to get 1,000. You can clearly see that in this case, it's going to positive infinity. The numbers just keep getting bigger and bigger and bigger. If I try to do the flip now, minus 0.1, 1 over x is going to keep the negative, right? So this is going to give me negative 10. Minus 0.01, that's going to give me negative 100. Minus 0.0001, that's going to give me, oh, I put some zeros there. That's going to give me negative 10,000. Notice that these numbers are approaching negative infinity. They're getting bigger and bigger and bigger, but they're all negative, which means all the values are dropping. So notice that this and that, they're not the same thing, right? So in this case, I could say that the limit of 1 over x as I approach 0 does not exist, right? Whereas I can say for 1 over x squared, the answer is actually infinity. So the quicker, more efficient way that the 205 student should be able to do is to just be able to draw the picture, right? And in that case, you can literally just look at the picture and see what the y values are doing. Otherwise, you can just actually approach it by plugging in numbers and seeing what sort of behavior is happening, right? Now, if both of these things start to do the same thing, if both keep getting bigger and bigger and bigger, or both keep getting smaller and smaller and smaller, you know the answer is infinity, respectively negative infinity. Now, if both start doing different things, you know that the answer is it does not exist, right? And this is, again, using that idea that limits are talking about getting close to something. I'll never actually get to 0. That's actually, it's illegal to get there. But what about just getting closer to it from both directions? Look at what the y values are doing, right? Now I know in case 3, one of these will be the answer. It'll either be plus infinity or minus infinity or not exist. So I know that's what I'm looking for. Looking for if things are always get bigger and bigger, or they always get smaller and smaller, or there's no pattern, they do something different. Right? So that's what you do in case 3. That one's a little bit more nuanced. You kind of have to look at the function, and the trick here is to realize, oh, that's a square, so it's always going to give me a positive answer. So things will always get bigger, whether I'm positive or negative. It's going to actually behave the same way. Right? In the same way, just from that idea, you can actually guess about approaching 0 of 1 over x cubed. Does not exist. 1 over x fourth. Infinity. Minus 1 over x to the 6th. Negative infinity, as I'm approaching 0. Right? You can kind of see the idea of the fact that the even powers, they'll always do the same thing on both sides, while the odd powers, one will go positive, one will go negative. So that's the basic strategy for limits. So you're faced with a random limit on a test. First thing you try to do, plug in that x value. If that works, great. That's actually your answer. Second, if you can't actually plug in the x value right away, try to simplify so you can plug in the x value. Try to factor something and cancel the guy that's making trouble. Right? If that doesn't work, it means it's either an infinite answer or it does not exist. And in that case, graph it. Look at what the y values are doing. If you forget the graph, you can kind of do this kind of analysis, try to see how the numbers are behaving, and that will get you the answer of infinity or not infinity or negative infinity or does not exist. Any questions on the strategy? Any questions on limits so far?
So the positive limit will always be the same direction? Or say like an x squared? Or...
No, it depends entirely on the function. It depends on the function. So you have to be able to either graph that or know what it looks like. Right? The opposite would be true if I was looking at negative 1 over x squared, then the answer would be negative infinity. Right? So it's not always going to be infinity just because it's a square. Well, if there's a minus sign in front, it's always going to be negative. So in case 3, you have to really pay attention to what the function is doing. One of the easiest, quickest ways, if you actually remember how to graph it, is to actually graph it. So it's not a matter of, oh, it'll always do this or always do that. It really depends on what the thing looks like that you're looking at. With that idea, I think the next thing that we should talk about is certain properties of limits. So that's the strategy, right? So trying to attack a limit problem is a 3-step strategy, right? If I'm just asking to compute a limit, first try to plug in. If you get an answer, awesome. You just have to stop. You don't have to do anything. If you can't plug in, try to simplify. Maybe you can plug in later. You know, if that works, great. If not, then it means that it either doesn't exist or it's infinite, and draw a picture, plug in numbers, try to figure out what the y values are doing, because the limit is all about figuring out what the y values are doing. Let's talk now about properties of limits. So let's see the constant and suppose the limit as x approaches a of f of x and limit as x approaches a of g of x exists. Right. So these are just 2 random limits. Pretend that they actually give us an answer. The left and right sides agree and we can actually have an answer. C is just a constant. Right? So now we have the idea of how to approach limits of, yeah, if I give you a single function, you just analyze that function. But things can actually be more complicated. So let's talk about that. Then 1. If I take the limit of a constant times a function, it turns out that I can factor that constant out. And take the constant times the limit of the function. Right, so an example there. I know that since I know that the limit as x approaches 1 of 1 over x is actually 1, this means if someone were to multiply 1 over x by some number, let's say I took 5 times 1 over x, it turns out that's just going to be the same as 5 times the limit of 1 over x, which is just 5 times 1. So 5 would be your answer here. Right? So if you know how to deal with the function part and there's a constant in your way, just move him out, deal with this guy on its own, and then you can multiply the constant later. Right? You could also try strategy 1 here. Just realize that this is actually just the same as the limit as x approaches 1 of 5 over x. And it's possible to plug in x equals 1 in that. You just plug in 1. You'd still get the answer 5. But the idea still holds that if you have a constant multiplying a function and you want to find the limit, you can just literally take the constant out of the way and not worry about it. And just multiply it at the end. So that's an example, right? So we know how to find some basic limits. We're trying to find limits of more complicated things now. The good news is limits actually obey the familiar laws of arithmetic, which means they actually distribute. There's a distributive law for limits. So 2, it turns out that the limit of the sum or the difference of 2 functions is actually the sum or the difference of the 2 limits. So if I have 2 functions being added together and I want to find the limit of the sum, I can actually just find the limit of each component separately and add those together. Limits actually distribute across sums. So that's pretty nice, right? Now remember, not everything distributes, so that's important. Powers don't distribute across sums. Logarithms do not distribute across sums. There are some examples, but limits actually do. So you can kind of do what you feel like here. So for example, if I asked you, what is the limit as x approaches 1 of x squared plus 1 over x? Well, I can just look at that as the limit as x approaches 1 of x squared plus the limit as x approaches 1 of 1 over x. This one, I plug in 1, plus this one, I plug in 1, so the answer is 2. You could also just use strategy 1, but if you want to break it apart, it's also fine. You just see that the limit as x approaches 1 of this function is, there's no problem with plugging in x equals 1 everywhere all at once, so you can also do that. Well, the idea is you will always get the same answer if you break the limit. You can actually distribute a limit across a sum. Yes?
How do you know whether you're going to do plus or minus?
Oh, it'll be given.
Oh, okay.
It just
Okay.
corresponds with the sign. So if I had, it's something you're going to be asked. So I could say x squared minus 1 over x.
Okay.
Right? The idea is it's still going to be, in that case the answer would be 0. Right? This just means the sign, it follows the sign. So if it's pluses in between, it'll be pluses over here. If it's negatives in between, it'll be negatives over here. Right? It actually just distributes in the normal sense of the distributive law. So limits actually distribute across sums, so that's nice. So constants, you can factor them out. If you have a sum, you can distribute it and just work on one at a time. Interestingly enough, property 3 is that limits actually distribute across products as well. So the limit of f of x times g of x is actually equal to the limit of f of x times the limit of g of x. Limit as x approaches, let's say 2 of x times the radical of x squared plus 1. So here I have two functions being multiplied. I have the function x multiplying the function radical of x squared plus 1. Turns out in my limit, I can think of this as x times the limit of the radical of x squared plus 1. Now in the first case, the limit is just 2, because I can plug it in, times, in this case, again I can just plug it in, I can just plug in 2, I get radical 5. So the answer here is 2 radical 5. Again, it's worth mentioning, this is why the strategy is so awesome. Strategy 1 would work again. If you didn't even think about it this way, strategy 1 would just work, because there's no problem with plugging in x equals 2 into this function. It's defined at x equals 2. So I could literally just plug in 2 here, plug in 2 here, and I'd still get the answer of 2 radical 5. But the idea is, if you wanted to distribute the limits, it's fine, it'll actually work out. Again, here we have property 4. Limits actually distribute across divisions. So limit as x approaches a of f of x over g of x is actually equal to the limit of the f divided by the limit of the g. Provided, of course, the limit of the g is non-zero. You can never actually divide by 0. So, example here, the limit as x approaches 2 of x over x squared plus 1. Well, I can think of this as just the limit as x approaches 2 of x divided by the limit as x approaches 2 of x squared plus 1. So on the top, I would get 2. On the bottom, I would again get 5. That answer is 2/5. So I'm going to say the limit of the top versus the limit of the bottom. And plug them in. Since the limit of the bottom is non-zero, that's my answer. Again, strategy 1 would also work. If I have limit as x approaches 2 of x over x squared plus 1, notice that 2 is actually the domain of this function. If I think of it as one function as opposed to the division of functions, 2 is in the domain. I can literally just plug in 2 everywhere, and I would get 2/5 again. But if I wanted to distribute the limits, I could. It will be valid, and I would get the correct answer. Another property. Limits also distribute across powers. So if I have f of x, well, it goes inside powers. Let's say I have a function and I raise to a power, then that's actually the same as the limit of that function raised to that power. So if I have limit as x approaches 3 of x squared plus 4 raised to the cube, I could actually think of that as the limit as x approaches 3 of x squared plus 4, and then cube that answer. So on the inside, I can just plug in 3, probably 9 plus 4. 9 plus 4 is going to be 13, so the answer here would be 13 cubed. Strategy 1 still works. So if I'm faced with this guy, limit as x approaches 3 of x squared plus 4 cubed. Notice that 3 is in the domain of this. I can literally just plug in 3 and not worry about it. 3 squared plus 4 cubed equals 13 cubed. You get the same answer. So in other words, whenever the function actually exists at the x value, the easiest thing to do is just plug in the x value and not worry about it. Any questions on these so far? So basically I said all that to say you can ignore everything I just said for the past 10 minutes and use strategy 1. But it's nice to know several ways to do something in case you forget one way, you can piggyback on another way. But yeah, limits are actually nice. They distribute across sums, across products, across divisions, constants, you can factor them out. They're really nice things to actually do. You don't have to worry about, oh, is this illegal? Odds are it won't be illegal. Limits they're very well-behaved things to some extent. Let's look at another example. Here. Limit as x approaches 0 of 4 plus x minus 2 over x. Ideas? First thing you do, step 1, try to plug it in. Can't do that. There's an x on the bottom. Divide division by 0. Step 2, try to simplify it to see if you can plug in 0. How does that work? How would you go about trying to simplify this? Ideas? Can this be simplified, or is it just hopeless? It's just hopeless. Just throw in the towel. Forget it. Give up. I'm gonna fail. Life's over. Ideas?
Multiply by the different squares. 4 plus x minus 2. You could do the opposite. So you have a negative radical 4 plus x plus 2. Then
Right, that's called the conjugate.
Yeah, conjugate.
So you multiply and divide by the conjugate would be one strategy you might try. So if you have two terms and one has a radical, you can just change the middle sign and try to see if that will work. So let's see what happens here. 4x minus 2 over x. So I'm going to multiply and divide by the conjugate. Right, this is like rationalizing the numerator. So I change that middle sign. Now what's going to happen?
You have to rationalize.
So the denominator becomes just x times this guy, 4 plus x plus 2. What happens to the numerator? Of course you can do that. I can multiply this by that. What's stopping me? It's difference of squares, right? This is like a minus b, this is a plus b. That's the whole reason why I did it, right? That's why the conjugate actually works. Because this allows me to square each term. So the answer is going to be a squared, right? Which is just 4 plus x minus b squared, which is 4. Now I'm going to have that 4 minus 4, so the 4's will die. So I'm left with x over x times 4 plus x plus 2. X's will cancel, right? And I'd be left with 1 over the radical of 4 plus x plus 2. Now what? Now I can actually plug in 0, right? I don't divide by 0 if I plug in 0. So if I plug in x equals 0, at this point I would just get radical 4 plus 2, which is just 1 over 2 plus 2. I'm just writing down all this stuff. You know what? equals 1 over 4. Right? A quarter is actually the answer. Some things I want to mention here. So rationalizing is one technique you have to remember from algebra. It will come in handy. So usually if you have a square root somewhere and you have two terms, rationalizing might be a good idea to break things down for you to a point where you can actually do things. But something else I want to note that's very important. Note keep writing the limit sign until you actually take the limit. This might be plug-in or otherwise. So notice here when you're given this problem, right? You start to simplify, but the thing is you're not actually plugging in x equals 0 yet. You're not approaching anything, you're just rewriting. So this limit hasn't been applied. So I keep writing it because I haven't applied it yet. I keep writing it, keep writing it. At this point is where I finally plug in x equals 0. At that point, I don't have to write it anymore. But notice that the whole time I had to keep writing this. Because I never actually let x approach 0. This whole time I was just simplifying. Now I get to a point where, hey, now it's convenient to actually see if the limit, I can plug in and take the limit. Because I did this whole simplifying thing, so let's see if it works out. And now I plug in x equals 0, and I don't need to take the limit anymore, because I just did take the limit. Right? Another thing I guess is there's a reason why I've been emphasizing algebra for a long time. Any simplifying technique from algebra, rationalizing, difference of squares, factor by grouping, any kind of thing that you can simplify to get something nicer to use is fair game, right? You can't be like, oh, how can you ask us to rationalize? I didn't do that since high school. No, it's still algebra. I can ask you. It's fair game. Algebra is important. So when you see something like this and you try to plug in, you realize you can't plug in, then you try to think simplify. You have to remember things like that. Oh, there's this whole thing about a conjugate, right? You have to have an idea of how to approach something. So another limit as x approaches 2. No, I think I actually want limit as x approaches 0. 1 over x plus 2 minus 2 over x. How do you do that one?
LCD.
Find the LCD. What is the LCD here? And so we have one denominator is x plus 2, another denominator is 2, the other denominator is 1. What's the LCD of all the denominators? 2 times x plus 2. So it's a complex fraction. The quickest way to simplify those is to multiply by the LCD over itself. So I multiply by 2 times x plus 2 over 2 times x plus 2. And let's see if this works out, right? So the first step is I try to plug in x equals 0, but there's an x in the denominator I can't plug in 0. So now I'm going to try to simplify. And then I realize, oh, it's a complex fraction. Maybe if I combined all the fractions, this would be something nicer. So that's what I'm actually doing here. So the quickest way to combine a complex fraction, which is when you have fractions inside of a whole bigger fraction, is to multiply top and bottom by the LCD. So now if I take this guy and I multiply that I write the limit sign because I'm not actually taking the limit yet, I'm simplifying. So if I take this times that, what's going to happen is the x plus 2's are going to cancel, and I'm going to end up with just the 2 times 1, which is 2. Minus, if I multiply this times that, the 2's are going to cancel, and I'm just going to be left with an x plus 2 times a 1. Parentheses. Right. Remember, every time you come after a minus sign, just open parentheses. Over, the denominator will be x times 2 times x plus 2. Now what actually happens in the numerator? So remember, we're simplifying a fraction, and we remember from algebra class, you've never wanted to expand the denominator. So that's not even something you think of doing at this point. So we're calculus students, we're big kids now. So at this point, I still can't plug in x equals 0 because this x is here. What else can I do? Well, it has to be something with the numerator is what you would do, because you never try to do anything with the denominator in this case. So what I can do is start to expand this. I would get minus x minus 2, and then this 2 will actually put that 2, and I end up with a minus x on top, over x times 2 times x plus 2. Right. Now at this point, there's only multiplication at the top and the bottom. I can actually start canceling stuff. So this gives me the following. Limit as x approaches 0 of, I would be left over with minus 1 over 2 times x plus 2. And at this point, I can actually plug in x equals 0. So I'm going to do that. Now I can drop the limit because I'm actually going to take the limit. I'm plugging in 0 because it's fine to do that now. The answer is minus 1 over 4. Questions? So I gave you this. The first thing you're going to try to do is plug in that x value. Couldn't do that here, so I'm going to try to simplify. It's a complex fraction. I know to simplify those, multiply by LCD over itself. I get to this stage. At this stage, I still can't plug in x equals 0, so it means my simplification isn't done. So I can't do anything with the denominator because you never expand the denominator when simplifying a fraction. So I work on the numerator, start expanding stuff. I found out, oh, the 2's kill each other, and I'm just left with x. And at this point, I can cancel the x's, and then I'm here. So this is fully simplified as far as it can possibly go, right? So now I'm going to try to plug in that x, and in this case, it works out, and I would get that answer. It's also possible that even after doing all that at this point, I still can't plug in 0, in which case, look at the graph. What is it doing? Plug in numbers, try to figure out what's going on. But in this case, it actually worked out, so that would be the answer. What else do we want to talk about here? Infinite limits and limits at infinity. Let's actually do that. This comes in handy in a variety of places, including later on in the semester when we're doing curve sketching. We'll need to compute infinite limits and limits at infinity. Can I get rid of this? For now, let me just write down what these are. An infinite limit just a limit where the answer is plus or minus infinity. We've actually seen one of these before. Example, the limit as x approaches 0 of 1 over x squared is infinity. I call this an infinite limit because the answer is infinity. Right? The answer is infinite. I call it an infinite limit. A limit at infinity is a slightly different concept. this is a limit where the x value approaches infinity. Right? So it's probably a little bit crazy to see if you've never, especially if you've never seen limits before, but it's possible that the value I want my x to approach to be infinity. So it would look like something like x approaches infinity of f of x, or limit as x approaches negative infinity of f of x. Such a concept is possible. Right? So let's actually look at something like that. So what would something like this mean? Let's do an example. What is the limit as x approach infinity of, let's again look at 1 over x. So it's my y value, it's my x-axis. And this keeps going down. Okay. So what could this possibly mean? What do you think the answer would be? Why do you say 0? How are you thinking of that? How are you thinking if x goes to infinity? Conceptually, what do you think that means? Well, the x values are running along this axis, so going to infinity means going where? Going to the right, right? Just keep going to the right. Keep going that way. Just keep going. When you think you're there, just keep going. Just keep going to the right. So this is saying, as I think my x values are getting larger and 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 even larger, what's happening to the y values? Well, all my y values are getting closer to 0, right? At any given time, if I plot a point here and I trace back my y value, it's actually closer to 0, right? At here, it's here. If I move over here, it's here. If I move over here, it's here. My y values are decreasing. But they're not decreasing forever. They're decreasing towards this point. Now, they'll never actually get there, right? But remember, limits don't actually care about getting there, but that's what they're getting close to. All my y values along this curve are getting closer to 0. So limit as x approaches infinity is saying, what is happening to my y values as I move far to the right? Right? And the answer here would be 0. So what you think of this as, what is y doing as I move far to the right? That's kind of the answer you want to get at that. Let's look at another idea. What about the limit as x approaches negative infinity of e to the x? First of all, what does e to the x look like? Right, like this. What's this intersection? 1, right? Now, as I move to negative infinity, what does that mean? Well, x is on this axis. Negative just means you go to the negative direction, far to the negative direction. Now, if you look at what this function is doing, what's happening to the y values as I move far to the right, to the left? They're approaching 0. This is 0 again, right? So this is basically asking, when I talk about limit as x approaches negative infinity, I'm asking what is happening to the y values as I move far to the left. Far to the left. So I don't mean as I move to the left right here, or as I move to the left right here. No, I mean far to the left, like far, right? Like really far. right? Just keep going and see what the y values are doing, right? Now in this case, these two answers were finite answers. They actually gave me a number. It's also possible to not have a number. It's possible for a limit at infinity to also be an infinite limit. For example, if I go from x approaches infinity of e to the x, I get a different story. Right? Now I remember the graph looks like this. Now if I ask you, what is the y value doing as I move far to the right? Y values keep going up, and they're going to keep going up forever. The farther up to the right I go, the higher up the y value is going to be. So here I can say that the limit as x approaches infinity of e to the x is infinity. So that's the notion of an infinite limit or a limit at infinity. Sometimes we can let the x values themselves increase without bound or decrease without bound. Get bigger and bigger and bigger, or get smaller and smaller and smaller. Sometimes we care about moving far to the right or far to the left and figuring out what happens. Right, and this idea is responsible for so many things you wouldn't even believe. So there are a lot of theories of it, especially if you look at like physics or something, and you can believe about, and you can talk about, you know, what's the age of the universe? Well, you can measure how fast the universe is expanding right now, and you can say, well, if we backtracked, you know, when we went far to the left back in time, if we assume the expansion was happening the same, it would actually take us like, you know, 13 billion years to get to this point. And so they just come with that age. The universe is 13 billion years. It's not a random number. It's a pattern that they are measuring right now. And they assume that that pattern always existed. And so they went far to negative infinity. And they're like, the starting point would have been around 13 billion years, right? So a lot of science actually refers up to this idea, and as well as, you know, they can predict far to the right. They can say, well, our sun is going to die in like 5 billion years, and we're all going to die in 5 billion years, because they can measure how much hydrogen the sun is using up ever so often, and they can say, well, if we keep track of this, you know, just keep going for a long, long time, it turns out we can get to this point, right? So the idea of, it's not a crazy idea, even though it seems that way. It just means going far in the future or far in the past and trying to analyze, based on what is happening right now in a window that you can see, what will happen way down there in a window that you can't see. And you can make predictions based on that. Right? So limits actually can capture that notion as well. So it's about what's happening as you get close to infinity or close to negative infinity, right? So it's not as nonsensical as you can think, because we never actually care about getting there, because we can't actually get there, right? But getting close to there, close enough, is going to be the idea. Now let's talk about continuity, a very important idea with limits. Any questions on this before I move on, or is it okay? So,
I have a question.
yes.
How quickly you put up the block? And how soon you cut the block?
Probably tomorrow, because by the time I get home, it's not right now we don't have to worry about this too much, because it's not going to be on the test or anything. So we don't have to worry. We're in chapter 2 now. The test is only on chapter 1. So there's kind of no rush for this right now. So.
Put the quiz on there.
You mean the quiz on Monday?
Yes.
No. No, I'll make the quiz on Monday on chapter 1 stuff as well. I might make some of this bonus, but not. So the quiz on Monday, I'll kind of gear towards preparing you even more for the test, giving you more examples of the kind of things that might come on the test. Yeah, so let's keep going. Continue. intuitively, right, continuous just means it keeps going, right? So intuitively what this means on some interval there's no break. We can graph a function without lifting our pencil off the page or pen. Right, so for example, I can say, here's a function a and b, and I can say something like this. That's my f of x. And I can say here, f of x is continuous on AB. Right? So I can say in this region of space that I'm looking at, I can literally graph my function without lifting my pencil off the page. Right? However, in another case, I can say on AB, my function can look like this. There can be a hole in that function. Right? So it means that to actually graph this in this region on this interval, I'd have to go here, I have to lift my pencil off the page, skip, jump over that gap, and then continue drawing. So in this it says f of x is not continuous. Right? It doesn't continually move. Right? Because there is a point where the function misbehaves. It's a gap, or it's an asymptote, or something like that. Not continuous. Another idea where it would not be continuous would be in the case of asymptotes, like a log or something. So here's my a and here's my b, and my function does this in between a and b. I can say it's not continuous because I have to start here, go all the way up, lift my pencil up, come here, and start doing this. So this is another case of not being continuous in some region. Now, telling whether we're continuous or not in some region is super easy to tell from a graph, from a picture. You can just look at it. To draw that, I would have to lift my pencil off the page. Sometimes, though, if you're given a formula, and the formula is sufficiently complicated, and you can't graph it, or you'd rather not graph it, it turns out you can still tell when this kind of behavior happens from when it doesn't. Right? And we can actually identify where we're continuous using limits. Later I'll mention why knowing if something is continuous is going to be important, but for now let's actually figure out how to tell if it is or not. We say, so let's give you a definition. We say f of x is continuous at a point x equals a. So here I'm talking about continuous at a point if the limit as x approaches a of that function is just equal to f of a. Right? Meaning, if the formula is one of those guys where you can compute the limit by just plugging in the number without doing any simplification, it's actually continuous at that point. It means that you'll be able to draw that picture without lifting your pencil off the page on some region that includes a. We say f of x is continuous. Just continuous in general, not necessarily at a point, if it is continuous at all points in its domain. So if this behavior happens literally at any point along the function, we say overall this function is a continuous function. So something like this, it's not continuous overall, but it is continuous at some point. It's continuous at here, for example. Because in this region I can draw it without lifting the pencil off the page. But I can't do it everywhere. Right? So this function would be continuous. This function, well, it depends on where you're looking. It's continuous over here, and it's continuous over there, but overall it's not continuous. Right? So that's the difference between continuous at a point versus continuous in general. We say in the classic mathematical fashion of defining something in the negatory, f of x is discontinuous if, I'm defining the phrase discontinuous, if it is not continuous. So another way of saying not continuous is the description discontinuous. So saying f of x is discontinuous somewhere is the same as saying it's not continuous there. Right? And not continuous means this equation does not hold. If this equation works, it's continuous. If this equation does not work, it's not continuous. Note, based on what we know about limits, 3 things need to happen here. One, f of a must be defined. You have to be able to plug in a into your function and get an answer, right? And by defined, I'm going to emphasize not plus or minus infinity. It has to give us a number as the answer, right? So that's one thing. It has to be defined. 2, right? So that makes sure that the right side of this equation is actually a number that makes sense. 2 is worrying about the left side of the equation. Limit as you approach a from the right, and limit as you approach a from the left of f of x must exist. Right? Because I need both of them to exist for this guy to exist, and they have to be equal. So that's the next thing that has to fall into place. And 3, both 1 and 2 must give the same answer. So there are 3 places that something can mess up being continuous. 1, it can just not be defined at the point that I care about, in which case it's not continuous. Or one of these limits cannot exist, or maybe they exist and they're a different number, right? And that would make it not continuous. But assuming that they are equal, then this will give me an answer, and step 1 would give me an answer. The third thing I need to verify is that those 2 answers are exactly the same thing, right? Because I need this side to be the same as that side. So if this gives me an answer 5, and this gives me an answer 3, it's not continuous, right? Because they must match up. So we don't have a time to go through any specific examples here, so let me just give you some pictorial illustrations. So for example, here's an example of a function that's not continuous, right? Because of this guy. What happens here? Your f of a not defined. Right? So it's not continuous here. Or you can have something like this. I can be defined at a, but let's say I'm defined to be some other number, like that. then again it's not continuous. Right here, f of a is actually defined. Limit of as x approaches a exists. Right? Because coming from the left and right, they will both give me this answer. This y value will give me the limit answer. Right? But my f of a is up here. So they're not the same. So not continuous. And you can notice that to draw this picture, I have to lift my pencil off the page, fill in that point, come back, and start drawing again. Right? I couldn't actually draw that without lifting up my pencil. Right? I can't draw this without lifting up my pencil either. Continuity is when the stars align, your function is defined, and it's actually defined to be exactly what the limit is. Right? So in this case, as I'm approaching a, my limit and the value of my function are actually the same number. Whenever that happens, it means I can literally just draw through any point along this curve. I wouldn't have to lift my pencil. Right, so here, you see that f of a defined, the limit of f of x exists, and you see that the limit actually equals the value of the function. When all those three things happen, it means there's a continuity to this function. I can just keep drawing and not worry about it, right? As opposed to if any one of these things don't work out, another case would be something like this. Here, f of a defined, but the limit does not exist. Right? Because my right side and my left side would give me a different answer. And the result is I have to lift my pencil off the page in order to start drawing that. Right? So it turns out once these three things exist, it necessarily means I can draw this without lifting my pencil off the page. If any one of those three things mess up, I end up with some kind of crazy situation where I can't draw without lifting my pencil off the page. Essentially why this is important is we can only do calculus on things that are continuous. If there's a gap, calculus breaks down, right? So figuring out when these gaps happen is going to be something that's important for us. And we'll stop there. We'll pick up next time on Monday. We'll have a quiz on chapter 1 stuff on Monday because the test is on Wednesday, and we'll continue on this. Remember to do the review, it's already on the website, and you can, maybe I'll carve out some time next class to answer some questions on that. And I will see you on Monday.